is a question that actually is quite recent compared to some mathematical questions. And that started, I would say, in the early 60s and still good to nowadays. So in the 60s, we started to have these first computers. A lot of these computers, and nowadays we kind of love when they came of this equipment, because our mobile phones are more powerful than these guys. But still, they were able to develop some algorithms that actually changed a little bit the way we see the world and how we optimize and find solutions to problems of real life. And they noticed also that these computers have some limitations. So they have some computational and hardware-specific limitations, of course, that we started to overcome over the years, but also some more theoretical limitations. And the larger the computer didn't mean that it could solve more problems, or not as expected at least. And so the researchers started to believe that maybe there was something more, and just not a big computer will solve everything, basically. So these are not laundry machines, these are indeed computers. And so what they started to realize is that they had efficient algorithm for some problems, and they didn't have efficient algorithm for other problems. So they wanted to classify the problems based on whether or not they could solve the problems efficiently. So this classification started by finding efficient algorithm for some problems. So here we have multiplication, shortest path when you're given a map and two cities in the map, and you want to find the shortest path between two cities, testing if a number is prime, or sorting a bunch of integers. All of these algorithms were effective, efficient, and so all of these problems were easy to solve in some sense. And we knew also that some problems, for instance, the perfect strategy chess, these were problems that not only were hard to solve on computers, but we could prove, we could have a theoretical approach to show that no computers, as we know them, and it's still true today, could solve this problem perfectly and efficiently. And despite this, it seems like a normal dichotomy, we had a bunch of problems for which we didn't know. And so the question was, well, are we missing a proof to show that these problems are actually hard to solve? Or are we missing a good algorithm to show that these problems actually can be solved efficiently? And for some of them, well, for instance, the discrete Fourier transform, after a while, we could find some efficient algorithm and put them in the easy to solve category. But still, we still have these problems in the middle and we don't know what to do with them. And still nowadays, this is an open problem on whether they admit an efficient algorithm or if we could prove that these problems are hard to solve. So instead of looking at the differences in terms of complexity of finding a solution, the researchers started to believe that maybe we should look at what is the complexity of checking whether a solution is a good, valid solution. And so if you start doing this way, well, then the problems which are hard to solve are actually also hard to check whether a given solution is valid. But these problems in the middle share the same property as the ones which are easy to solve, that it is easy to check a solution. So what does it mean easy to check a solution? It means that if I give you a solution and you don't trust me, basically, you can check yourself. So for the Sudoku, you give me a partially filled grid, and I have to complete it. And if I complete it and I give you this grid, you can check efficiently whether it's a good solution or not. And all of these problems have this property. And the question is, well, then because we can check efficiently whether a solution is valid, can we also find such a solution? So now that I defined this problem a little bit informally, I'll give a bit more formality to this. So P is the class of problems for which we can solve the problem efficiently. And when I say, well, I said we, but I didn't write we, because they can be solved efficiently. So probably there are problems in P for which we don't know yet, right? It's not that because we know the algorithm. If we know the algorithm, when we can say it's in P, but it is or it is not in P. That's different. And so P stands for deterministic polynomial time. So this efficiently here means indeed in polynomial time with respect to the size of the input that you give to the problem. Now the class NP is the class of problems whose solution can be checked efficiently, and NP stands for non-deterministic polynomial time. So all of this works in the Turing machine, deterministic or non-deterministic, but we can think of Turing machines as just basic computers. And so efficiently means in polynomial time, as I mentioned. So every problem in P is also in NP, because if you're able to find the solution, you're also able to check whether this is a solution. Otherwise, you wouldn't be able even to recognize what you're doing in some sense. And the question, the P versus NP, can be stated this way. It asks whether finding a solution is. So for the rest of the talk, we're going to focus on these problems in NP and try to understand a bit better how to solve this question also. So before being able to actually talk about this P versus NP question in detail, I have to go through a bit more definitions. So we say that the problem is NP hard if it is as hard as any other problem in NP. And I mean that you could find any problem in NP, take its input, efficiently translate this input into an input of your NP hard problem. And then if you had a solution for your NP hard problem, you could translate back to a solution of your problem in NP. This is what it means to be NP hard. And we knew already back then in the 60s and early 70s that we had some NP hard problems. Now, I said we would focus on problems in NP. And at the moment, nothing guarantees that the problem is within NP. Maybe checking a solution is hard, actually. So we say that the problem is NP complete if it is NP hard, as defined above, and also belongs to this class NP. So in some sense, it means that not only the solutions can be checked efficiently, but every problem in NP can be modified, every input can be translated into an instance of an NP-complete problem. And if you had a way to solve this NP-complete problem, then you would also solve every other problem in NP. And if you do this efficiently, because this translation of the input and the solutions can be done efficiently, you would actually do everything efficiently. So an efficient algorithm for an NP-complete problem would provide you with an efficient algorithm for every problem in NP. And so this means that because the long-standing question P versus NP is still open, it means that we don't have actually an efficient algorithm for NP-complete problems, for none of them. And it would be enough, we will see how, to actually provide just one efficient algorithm for any NP-complete problem to show that P is equals to NP. And so in these times, this was the Cold War. So I'm talking about 71, 72, and 73. These two guys, they didn't know each other. Stephen Cook is an American-Canadian researcher, and Leonid Levin is well, he's born in actual Ukraine, current Ukraine, and so he was a Soviet researcher. And they independently provided a proof, which is known today as the Cook-Levin theorem. So there is only 2 years of difference, which is quite extraordinary. But there is a problem which is NP-complete. Although we defined this notion of NP-completeness for a problem to be NP-complete, nothing guaranteed that there was such a problem. And they proved that, yes, there is such a problem. And this is probably the most important and major result in theoretical computer science still nowadays. It means really that every problem in NP can be translated into an instance of this problem here, satisfiability. And that if you're able to solve this problem efficiently, you will solve every problem in NP efficiently. So what is this satisfiability problem? You're given a Boolean expression. I'm going to give an example. So it's just a bunch of variables that can be set to true or to false. And you have n and ors in between. And you just have these to evaluate. And you have to give a value, true or false, to your variables. And you have to decide whether the formula, this Boolean expression, can be evaluated to true. So for instance, right here, phi is a Boolean expression with 3 variables. And when I have a bar over, for instance, over x1 here, it means that I look at the opposite value to which x1 has been set. So if I set x1 to true, x2 to true, and x3 to false, then I can look that within my parentheses, everything will be evaluated to true. So here x1 will do the job. Here x2 is set to true, so it will satisfy this bit. And for instance, this one here, x1 will also be fine. But this one here at the end, it's because there is a bar over x3. So I look at the opposite of the value of x3, and this is false. It evaluates to true. And so this formula is satisfied by this assignment. So, okay, we have one witness, we have one problem, which is in NP and NP hard, that is NP complete. And if we could solve this problem efficiently, we could solve it one efficiently. But this is just one problem. And well, the first proof, right, in 71, really motivated Richard Kraft, showed just a year later, which is really short for such an idea, that actually there are many other problems. He proved 20 other problems in NP are actually NP complete. And these were the kind of problems that we had in the middle before. They are not hard to solve, or at least we cannot provide a proof, and we cannot find an efficient algorithm. And he showed that basically they are equivalent to satisfiability. They are all comparable in terms of complexity. And instead of providing a proof that would again be long and fastidious to show that these problems are can generalize every problem in NP, like Cook and Levin did, what he did is that he said, give me an input for satisfiability, I'll transform it into an input of my problem, one of these 21 problems, efficiently, and if I can have a solution for this problem of mine, then I could translate it back efficiently into a solution for satisfiability. And this is this concept of polynomial time reduction. So this is what I've said since the beginning, just an efficient translation. And so nowadays, actually, we know thousands of problems that are NP complete. And the technique, of course, is not to redo the job of Cook and Levin, but just to do what Karp did by providing this polynomial time reduction, so these translations of input and solutions efficiently. So we only know exponential algorithms for NP-complete problems. Actually, if we knew a polynomial time algorithm, then we would show that P equals to NP. So every time you're facing an NP-complete problem, and in real life there are many, the hope, assuming that P is different than NP, would be to provide an algorithm which is exponential. So suppose that you want to solve satisfiability, right, the problems that we've seen, and you're given a Boolean expression which has n variables. So if you don't optimize or anything, you actually have 2 to the n possible combinations to check. For every variable, it's either true or false, and you have to check everything. And in the worst case, you have to check them all because maybe your assignment does not exist. Maybe there is no way to find an assignment that will satisfy this Boolean expression. So let's have a look at what it means to be exponential, right? So the input size here, so n variables, the number of steps roughly, or the number of combinations that you have to check, and an estimated time to solve. So I fixed, for instance, 10 variables. This is 2 to the 10th, is roughly 1,000 combinations to check. And the time to solve this one, I just fixed arbitrarily. I said, okay, my computer will take 0.01 second to solve this. Okay, this is just what I fixed. Of course, if you have a faster computer, maybe you divide this by 2, by 10, by 100, but as we'll see, it doesn't really matter. Because when you jump to 20, then you jump to 10 seconds. So we can see that actually the gap is roughly around 1,000, and there is some logic behind this. For 30 variables, then it's more than 2.9 hours. And I would say that this is still okay. If you have an NP-complete problem that you really want to solve, say a scheduling problem for a train station, if they have to wait 3 hours, in some cases, I would say this is still reasonable. But 30 here is really a small number of variables for a real-life problem, a real-life input. So when you jump to 40, then you already need more than 4 months. And this is not good. This is definitely not fine. And then just for the fun, right, if you have 50, which again would be a very small input, it's almost 350 years. And the gap is always because you multiply, I mean, you add 10 variables, then you have actually times 2 to the 10, which is roughly 1,000. So the gap is every time 1,000 times more time, right? The gap in between. This is really bad, and this is what this means to be exponential. So even if you were able on the computer to solve something in a few hours on the x variables, well, on 2x variable, then you will need way more. So this is really bad, and exponential is bad in general. So some fun NP hard and NP complete problems. So Sudoku is actually NP complete.
Now, I want to be slightly more precise here because Sudoku is not NP complete if all of the grids have bounded size, because then there is only a bounded number of ways to fill a Sudoku grid, and this would be fine. But if you generalize this Sudoku to n times n grids, right, for some value, then this is a problem which is NP complete. It also means that someone came up, I mean, this someone is Yato in 2003, came up with a polynomial time reduction that I don't know exactly from where it reduces, but the idea would be you take SAT, this satisfiability problem, and you transform an instance, a Boolean expression, into something like this. So this is something probably very clever. I didn't have a look at the proof, but this problem is NP complete, the generalized version. Candy Crush is NP hard. So NP hard means, well, it is as hard as every other problem in NP, but it's not necessarily in NP, right? So this is a bit more recent, 2014. Pac-Man is NP hard. Two Dots, this is a fantastic game. I spent a lot of time playing this game. This is NP complete. And Angry Birds, which I reinstalled yesterday evening, just to be very serious for this talk. So Angry Birds is actually NP complete. The original version is NP complete, and I think Angry Birds 2, and this screenshot is from Angry Birds 2, is actually NP hard, and I don't think it's NP complete. I don't think we have a proof of NP completeness. All right. So the complexity classes, if represented like this, will have two different shapes on whether P is equal or different than NP. So if P is different than NP, then we see that we have this class of problems P that we can solve efficiently. This is the problems NP, right, that we can, for which we can check a solution efficiently. And these are the NP complete problems we've been talking about the last 5 minutes, which are also NP hard, both in NP and NP hard. And if P is equals to NP, then we have a simpler picture, I would say. Everything here collapses into just one class, and NP, NP complete, or P are just the same classes. Now, interestingly, although we don't know if P is equal or different than NP, if it was different than NP, then Ladner showed that there would be problems which are neither NP nor NP complete. They would be in between here. And we actually have some candidates for these problems. For instance, graph isomorphism or prime factorization, where you want to give a factorization of a number into prime numbers. So this would be a problem that would be in between, probably, if P is different than NP. So I mentioned $1 million in the title. I have to talk about money. So the Clay Institute in 2000 opened this Millennium Prize problems. So they selected the 12 most important conjectures in mathematics. And we can see that we have P versus NP over there. And this is actually the latest conjecture also among all of them, right? The other ones have been open for many more years. And if you solve any of these problems, then you get $1 million. And I'm already sorry if you solved Poincaré conjecture yesterday, then someone did it before you. And so he solved it in 2003, but Perelman, the guy who came up with this solution, didn't claim the money. So maybe if you solve P versus NP, you can ask for $2 million, right? You can always bargain. So let's say you want this $1 million. How would you show that P is equals to NP? You have two different approaches. The first one would be to provide a proof, right? A lengthy proof, as we know them. And it would be possibly non-constructive in the sense that you could just say, suppose that P is different than NP and conclude a contradiction. And then you don't get anything but the fact that P is equals to NP and that's all. Or you could also find an efficient algorithm, so a polynomial time algorithm, for a problem which is NP complete. And then you actually, all the complexity classes collapses and you show that P is equals to NP this way. And this second option is, I think, why people believe that if P were equals to NP, then it would be simpler to prove that P is different than NP because we have this option here. And there are at least 62 papers claiming that P equals to NP. So the question is, why is it still an open problem if people have apparently solved it? Well, among these 62 papers, I didn't check them all, of course, but they are not submitted or accepted to publications in famous journals. And the reason sometimes is just that they lack details, or there are small typos that create big mistakes and gaps in the proofs. So these papers maybe will be patched someday, right? But at the moment, although these people claim that P equals to NP, the rest of the community do not believe that these papers are precise enough so that we could actually claim that P equals to NP. Now, if you want to show that P is different than NP, then you don't really have a choice. You need to provide a proof, and we don't have this joker card or just finding an efficient algorithm or something like this. This is just a basic proof now. And just to say that, I'm not saying that these guys are wrong, but I'm saying either these guys are wrong or these guys are wrong, because there are 50 papers claiming that P is different than NP, right? So someone must be wrong at some point. I'm not saying who. And so if you answer the P versus NP problem, please remember my name, contact me, we can do half-half, I don't mind. But a real tip for you, if you actually prove that P equals to NP, right? Not only you answer the question, but you prove it's equal, and you have an efficient algorithm to solve the NP complete problem, you should keep this for you. Because as we're gonna see, you'll be able to get way more than just $1 million this way. But you can tell me anyway, of course. So if we know that P is equals to NP, if you know that P equals to NP, you can, and you have a really efficient algorithm. I'll come back to this later. So I mean a polynomial time algorithm that is actually really efficient, right? Really not too bad for solving an NP complete problem. Then most of our current encryption algorithms actually could be broken. You could read internet like an open book. You could connect to your bank account and add $2 million if you want. You could do everything that you want because the encryption for you would not exist, basically. You could break everything in polynomial time, assuming that this is really efficient, of course. Problems that are easy would be just easy to check, would also be just easy to solve. And this would mean that for the humanity in general, we would have a tremendous, I mean, it would be an improvement over our lives that we don't know, we haven't seen yet, I think, in humanity. This could look like if today we didn't have any computers and tomorrow we had computers like we have today. This would be a great leap forward. Now, as I mentioned, right, really efficient here, I want to insist on the really, because what is possible is that P is equals to NP, but the time complexity to solve an NP complete problem would still be very, very bad. So it could be an input size of size n, and then you have n to the 10 to the 10 to the 10 to the 10 to the 10, and you count like this as many times as you want. And this is still polynomial because it's bounded, but there is no way any computer is going to solve this. And so there is no hope actually to make use of this to get even richer. In this case, I suggest that you just claim the $1 million. Now, if we only have a non-constructive proof to show that P is equals to NP, or that your algorithm is really not efficient, what does it happen in our lives? Well, it's still a scientific accomplishment, of course. A bit frustrating, maybe, because it means that, well, we will never be able to use this result to actually improve our lives. It's a bit of a shame. And yeah, nothing else really changes, but we should be ready, of course, to change our encryption algorithm, just in case someone comes up with a better algorithm and improve over the complexity. And if we know that P is different than NP, then it's just life as we know it today. Actually, it just convinces us that what we've been doing for decades is not so bad after all. And the improvement that we try to find for solving NP complete problems haven't been done in vain, right? That would still be a scientific accomplishment. And if you don't finish a Sudoku grid, you could say, well, I can blame P is different than NP. Now, I want just to show you that both ideas, P is equals to NP and P is different than NP, could be supported with some silly arguments you could argue, but that both options are at some point believable. So I want to play a game. It's called the number Scrabble game, and it's a two-player game. So you have to, every player take turn, and they have to select numbers from 1 to 9. They cannot select a number twice, and or selected by the other player. And the first one, which has 3 numbers that sum up to 15, wins the game. So taking 6 and 9 is not enough, right? Because it sums up to 15, but it's not 3 numbers. You want 3 numbers and they must sum up to 15. So say that player 1 plays 3 and player 2 selects 6, then player 1 selects 5. Now, how would you think player 2 is going to play? Well, he's going to say, okay, if player 1 takes 15 minus 3 minus 5, what is it? So it's a 15 minus 3 plus 5, 8, so it's 7. Then if I don't take the 7 now, player 1 will select 7 and win the game. So player 2 will take the 7 now. Now player 1 has to choose, and he's going to adopt the same strategy as saying, okay, 15 plus minus 6 minus 7, this is 2. Well, if I don't take 2 now, then player 2 will select it later and win the game. So he has to select 2. And if I scramble these numbers and create them, display them in like this in a square, this is called the magic square because it has the property that every row sum up to 15, every column sum up to 15, and the diagonals sum up to 15. Now we can see the game as, well, I want to select cells in this 3 by 3 grid such that I have a complete row, a complete column, or a complete diagonal. And this is a tic-tac-toe game. And my point here is that playing this game, when displayed just over one line, is not hard, okay? But it's definitely simpler. Here, if I say, okay, this is player 1 turns, what should it take? Well, it's clear that it has to take 2, because otherwise the green player, player 2, will get the first row. So it will take 2, and then this forces the green player to select 8, otherwise the diagonal will be available for player 1. So just this change of point of view makes the problem somehow a little bit easier to understand and to play. And maybe this is what we're missing with NP-complete problems. Maybe we just don't have the right point of view, and someone a bit more clever than we are, with a bright idea someday, will come up with a super nice idea and solve some NP-complete problem with an efficient algorithm. So this is believable, I think. And besides, this was the case for the discrete Fourier transform, for instance. We had problems that were in this middle, right? We knew that they couldn't be hard, or at least we didn't have a proof, and we couldn't come up with an efficient algorithm to solve them. And after a few decades of research, people actually showed that, yes, we can solve them efficiently. So I think that there's still hope, and that maybe the same story will appear for NP-complete problems. Now, supporting that P is different than NP is still a bit easier, I think. First of all, there are clever people who worked on these problems, or who worked in just complexity theory in general. And for 50 years, no one has ever been able to show that NP-complete problems would admit an efficient algorithm. So it kind of supports the fact that there is no such algorithm. And I want to share this quote from Scott Aronson, who is a theoretical computer scientist, who says that if P is equals to NP, then the world would be a profoundly different place than we usually assume it to be. There would be no special value in creative leaps, no fundamental gap between solving a problem and recognizing the solution once it's found. Everyone who could appreciate a symphony would be Mozart. Everyone who could follow a step-by-step argument would be Gauss. Everyone who could recognize a good investment strategy would be Warren Buffett. Of course, this quote has to be a little bit provocative, right, to make a point. But I think that's the idea, right? There is nothing, if you ask my students, they can check a solution in polynomial time, but finding one is definitely harder. And I think they would agree with Scott Aronson, but this is a bit weird if P is equals to NP. Now, you cannot cite Scott Aronson nowadays and just cite this one. You also have to cite this second quote. Given how many confusions and weird misinterpretations it's found, I, Scott Aronson, hereby formally disown my statement about how everyone who could appreciate a symphony would be Mozart if P equals to NP. This is because people were scandalized by hearing this, but I think they didn't have the right idea of what is this question, P versus NP. And I still believe this first quote is valid. Okay, so the last case, and this is the sad story. Maybe P versus NP cannot be proved. Maybe our logical theories of the moment cannot answer the question in either direction. And this is super frustrating, because this would mean that you and me could come up with a polynomial time algorithm for an NP-complete problem if P is equals to NP. But we wouldn't be able to prove that the algorithm is correct, although the algorithm would be written. And this is mind-blowing and frustrating, and I hope this is not the case somehow, because if there is an answer to this question, I would like to see it in my lifetime. And if it's not provable by our logical theories, there is no hope, right? But this is one possible case that had to be mentioned. Okay, so how do we solve these NP-hard and NP-complete problems? Because, as I said, we have many problems in our real life, scheduling at train stations, for instance, or vehicle routing issues, right, where you have a fleet of vehicles that you have to organize. The Amazon delivery man, right, he has to know who to visit first. And all of these problems are NP-complete and have exponential algorithms. And as we've seen before, even for small numbers, an exponential is bad. So how do you solve these NP-complete problems in general? We have different approaches. The first one is just using what we call heuristics. So these are algorithms that don't necessarily compute an optimal solution, but they try to be not too bad at computing a solution. So we have some heuristics that just say they follow the human reasoning, and they say, so they follow the intuition of a human. So the human writes an algorithm by observing that the inputs usually it's a good thing to do this. It's maybe not true in general, but for the inputs that you try to solve, it's fine. We have a bit more better heuristics, which I will call approximation algorithms. And these are just the idea of heuristics. It's the same, right? You try to compute a good solution, but you also have the guarantee that it's not too far away from an optimal one. And there are also in these approximation algorithms, the ones that the more time you wait, the more the closer you get to an optimal solution. And so it depends also how fast you want your solution, right? So there is a whole bunch of research in this direction. There is also the idea of focusing on different kind of input and specific inputs. So you could develop efficient, so polynomial time, and optimal algorithms for specific kind of inputs, which would, well, it doesn't mean that the problem is not NP-complete, but on some specific stuff, it might be easy, and maybe it's enough for your application. And lastly, there is a bunch of people just trying to decrease the base of the exponent here. So 2 to the n is really bad. This number to the n is also quite bad, but it is not as bad, and definitely not. And if you compare the graphs, this one grows way slower than this one when n increases. And lastly, because I thought that if I didn't talk about this, the talk would be missing something, I have to mention these quantum computers. I don't know much about quantum computing, but some people believe that quantum computers are going to change the world as we know it, and I want to say it's wrong. So BQP is the class of problem that can be solved efficiently with an error probability of at most 1/3, so basically in most of the cases, on a quantum computer, right? So you can solve on a quantum computer efficiently these problems in BQP. This corresponds to the class P for the normal computers in the quantum world. And this stands for bounded error quantum polynomial time. Now, this class BQP, we know it contains the set of problems in P. It means that if you can solve a problem efficiently on a normal computer, you can also solve it efficiently on a quantum computer. And it is believed, although we don't have a proof, that NP is not a subclass of BQP. This would mean that if P is different than NP, which is also believed with most of the researchers, that we would have a drawing like this, where we have NP-complete problems on one side, and BQP does not even touch these NP-complete problems, which are in some sense equivalent. So they're completely out. They contain problems in P, they contain problems in NP, which are not in P, right? It's a bit better. And interestingly, I think that's the most interesting fact here, is that they also contain, so it means that these quantum computers can solve problems efficiently, even though on a normal computer you cannot check if the solution is valid efficiently. So these are these problems on both sides here, which are outside of NP. And this is what we expect to be true, although we don't have a proof for that. And we know that we could solve some problems efficiently on quantum computers, and this includes a prime factorization. So this is the problem that we use for, or at least we rely on the complexity of this problem to ensure the fact that encryption is hard. And I'm simplifying stuff a little bit, but this is the idea. And actually, prime factorization here is one of these problems that would be in BQP and not in P, very likely not in P. But this can be solved on a quantum machine, on a quantum computer. And there are also something I don't mention on the slides, but some NP problems can be solved faster on the quantum machine. But it means that instead of taking 2 to the n steps, it takes 2 to the n over 2 steps. And you have to realize that these theoretical concepts also have to agree with the hardware that we have. And nowadays, the computers are quite powerful. And these quantum computers are not powerful. Theoretically, they are, but in practice, they are kind of slow. And so this 2 to the n over 2 doesn't mean that you will solve instances which are twice larger, because everything takes more time on a quantum computer. So this might be the future of computing, but it still doesn't answer the P versus NP question, and it still remains an important question with respect to the complexity of the problems, because we cannot solve NP-complete problems with quantum computers. And I'll conclude on this and receive your questions.